Morning. Nope. Good afternoon. Nailed it. Very smart. All right. So yesterday we talked about the geometric sequences and kind of what the explosive form is. We talked about the partial sums. Let me kind of scroll back through those. All right, this is our explosive form for a geometric sequence. Geometric just means that it's being multiplied by the same ratio each time. All right, and we call that ratio r, so it could be multiplied by 4 every time, or it could be multiplied by 2/5 every time, or anything. As long as it's the same thing that's being multiplied each time. And we also had a formula for partial sums of a geometric series. Okay, if I want to add up like the first 5 terms or the first 10 terms or 12 terms or whatever, then we can do the partial sum formula. So we did a couple examples of that. 5th partial sum, 7th partial sum, etc. So now let's take a look today at more specifically, because for arithmetic and geometric, they both have an explicit form. They both have partial sum formulas. But geometric series goes one step further in that it also has infinite sums. Okay, which is kind of strange. So let's talk about an infinite series. Right? An infinite series can do one of two things. It can diverge. So that means the sum of the series goes to positive or negative infinity. It means there is really no sum. Okay, so we can imagine something simple, like if I add up 1 plus 2 plus 3 plus 4 plus 5 plus 6, and I just keep doing that forever, am I ever going to hit like a maximum value? No, because I'm always still continuing to add more numbers to it. So this sum would just go to infinity, right? Positive infinity. Right, so that diverges. That's what we would say. So the other side of that coin is we can say that a series converges. The sum of the series goes to a limit, and we'll talk more about limits later on at the very end. And the limit is an actual number. So this is very counterintuitive, potentially, because, again, this is for an infinite series. So it's kind of hard to reconcile. How can I add up an infinite number of things but end up at just an actual number, right? Because up here, this sort of makes sense. Add up an infinite number of things. Well, you're not going to have an actual sum. It's just going to end up being infinity. But there are some series that will actually converge, that even when you add up an infinite amount of things, you'll end up with just a single, like, finite number. All right, it's kind of strange, but let me give an example that we're used to. So I'll write the series version of it first. So let's say 1 to infinity. So now usually we just have some number up here, but let's put infinity to say that we're going to have an infinite sum. We're never going to stop adding things. 1 over, actually, let's do 3. 3 over 10 to the nth power. Okay, so if I plug in 1, 3/10, and then if I plug in 2, so 3 over 100. If I plug in 3, so 3 over 1,000, etc. All right. Cassidy's alive. Damn. We were sad, Cassidy. I was kind of sad that you just abandoned me, abandoned us all, abandoned our whole class. We were all such good friends. We were making it through quarantine together, and all of a sudden Cassidy decided she didn't need us anymore. That was rough. 3/10, 0.3, 3/100, 0.03, 3,000ths, 0.003, etc. So if I add all of these up, 0.3 plus 0.03 plus 0.033 or 0.003, so I'm getting 0.333, etc. And I think you can kind of see here. So if I keep doing this pattern, I would just end up with 0.3 repeating. But you guys know what makes 0.3 repeating, right? 0.3 repeating is just 1/3. Right? That's how you guys have known that about 1/3 for, I don't know, years. If you do 1 divided by 3, your calculator says 0.333333333, right? And so it really is pretty interesting that you can, again, this is coming from adding up an infinite number of things. If you add up infinite pieces, you're still just ending up at a single number, right? A finite number, something like 1/3. All right, it's pretty crazy. So one quick thing that isn't in here. Your mind is blown, I know. So for a geometric series, there can be kind of two forms. So it could either be this times r to the n minus 1, or okay, so a couple key differences here. This one starts at 1, this one starts at 0. This one has n minus 1 as the exponent, this one just has n as the exponent. Okay, so these series still represent the same thing. All right, they are still the same. It's just a different way of writing it. Okay, so either the point is, though, this is still a1 is still always the first term, because you can think about, if we plug in 1 minus 1 is 0, r to the 0th power is just 1, so all that we have is a1 for that first term. Okay, or over here, if n is 0, we start by plugging in 0, so r to the 0th power, I'm still just left with a1. So these are both the same exact thing. I just lost my voice. These are both the same exact thing. It's just a different way of writing it, and we'll see examples that are in both formats. Okay, but either way, the point is that that first exponent ends up being 0 somehow. Okay, these are the most common ones we could see. Okay, so turns out geometric series are types of series that can converge, right? Arithmetic ones, well, I won't talk about arithmetic ones, but geometric series, we can easily determine if they'll converge just by looking at r. So if the ratio is less than 1, then the geometric series will converge. Okay. Yesterday I went to Target and didn't see you, so you've been lying to us. Which checkout line did you go to? Cassidy's always on. What are you always on, Cassidy? Probably on break. So our first example, the ratio. So just for, this is very simple. Just if the ratio is 2/5, well, guess what? 2/5, the absolute value of 2/5 is less than 1. So that geometric series converges. If the ratio is -3, absolute value of -3 is 3, right, which is greater than 1, right, but it only converges if it's less than 1. So since this is greater than 1, we know that this diverges. Right, if I added up all the terms, I'd get infinity or negative infinity. But if I added up all the terms of whatever this series would be, again, I don't even care about the other stuff, but as long as the ratio is less than 1, or the absolute value of the ratio is less than 1, then I know that the series will converge. Changes, but usually 1 or cleaning self-checkout. Breaks 15 minutes. Unrecognizable. Yeah, Cassidy, I heard you had a hair change. How do you feel about it? Sum. So, sum of a convergent infinite. So, remember, the only way that this formula works is if it converges. And the only way that it converges is if the absolute value of the ratio is less than 1. Okay, but it turns out to be actually pretty nice in that we just get this formula, which is fairly simple. Again, for adding up an infinite amount of things to just end up with this pretty basic formula, it's pretty intense. Okay. If possible, find the sum of the infinite series. All right. So, as I look at this, I can tell that, yes, this is in that format. Of a geometric series. So if it's a geometric series, that means that I just have to look at the ratio. So the ratio in this case is 1/2. Absolute value of 1/2 is less than 1. So I can say that the series converges. All right. Since the series converges, then that means we can use this formula to say what would the sum be. Right? What would that infinite sum end up being? If I could scroll down. So that series would equal, the formula is just a1 over 1 minus r. a1 in this case is -3. So -3 over 1 minus 1/2. One minus 1/2 is 1/2. I'm dividing by a fraction, so we of course know that that's the same thing as multiplying by the reciprocal. So -3 times 2 over 1, which is just -6. So again, a pretty basic answer. We've discovered, or not we've discovered, but we show, if we add up an infinite amount of terms that are of this format, plugging in 1, then plugging in 2, plugging in 3, plugging in 4, plugging in 5, and adding them all together forever, we end up at -6. That's pretty wild. I like it. Brain's literally exploding. Tough. You'd think Target would have some sort of anti-brain exploding helmet or something, you know? If possible, find the sum of the infinite series. Okay, so again. All right, now this looks a little different. All right, so first off, this is in, n equals 0. So I'm trying to see, is this of the form, so 0 to infinity, a1 r to the nth power. This sure doesn't look like that, right? But maybe it is. I might just have to do a little bit of changing, a little bit of manipulating. Matt is always here, Megan. You know this. How many times does he have to tell you? But I'm interested in this 2n plus 1. Two to the n plus 1 is the same thing as 2 times 2 to the n. Right? Because remember, exponent rules tell us if we have addition and an exponent, we can split it up into like two bases. You know, in the same way that x to the fifth is the same thing as, you know, x squared times x cubed. Right? Because 2 plus 3 is 5. So if n plus 1. Okay, so this is something I could do. And in the denominator, I still have 5 to the n. Okay, and now I especially am noticing that in the numerator, I have something with an exponent of n, and in the denominator, I have something that's also an exponent of n. Now that's different, right? I have a 2 and a 5, but he sits in the shadows waiting, much like Ted Bundy. Twitch Ted Bundy in this chat and Ted Bundy in real life, unfortunately. Both, they have a lot of commonalities. 2 to the n over 5 to the n. We can use our exponent rules to rewrite that as this. Right? Because if there's a fraction all to an exponent, that just means the numerator gets the exponent and the denominator gets the exponent. So 2 to the n over 5 to the n. It's the same thing. So now when I look at this and this, it looks a lot more similar. Right? And it looks like this is now in the correct form that I can see that, hey, yes, this is a geometric series. So since it is a geometric series, now I can start to look at, okay, does this converge or diverge? Well, convergence is based upon the ratio. So if my ratio is 2/5, absolute value of 2/5 is less than 1, which means that this series converges. Since it converges, then that means we can use this formula. That means this whole series, this infinite series, actually just equals a1 over 1 minus r. a1 is 2. 1 minus r, so that's 1 minus 2/5. Let's just do a little bit of fraction work. 2 over 1 minus 2/5, so that'd be 3/5. Instead of dividing by a fraction, multiply by the reciprocal, so 2 times 5/3. 2 times 5 is 10. 10/3. I missed a lot over here. Okay, time to catch. I watched the Zac Efron Ted Buddy movie with my mom last week. Was it good? Yes, it is good. Zac Efron is a good actor. Zac Efron is so cute. He was superior in High School Musical 2 and 3. A lot of hot takes in there. So this is our infinite sum. And again, this formula only works if we can show that the geometric series converges. If the geometric series diverges, if we get a number that's the absolute value is greater than 1, then we cannot use this formula. We would just say the series diverges. Find the sum of the infinite series. Okay, so I'm not even given an equation here. I'm just given the actual series itself. But I can figure out the pieces I need. So first of all, I know I need A1. There's A1. Next, to know if this is even possible to do, I need to figure out what's the ratio. All right, so I'll divide 9/2 divided by 6. So it's 9/2 times 1/6, which is 9/12, which is 3/4. Okay, now, so this is my potential ratio. Not my ratio? I think so. But let me check my other ones as well, because again, we want to make sure that this is actually the ratio. So I'll divide the next two terms. So 27/8 divided by 9/2. So 27/8 times 2/9. So 27 would cancel with the 9, so that would be 3. 8 would cancel with the 2, so that would be 4. Yeah. So also 3/4. I don't know why I'm writing like I'm slowly falling down a hill. Okay, and I could check and do the same thing. 81/32 divided by 27/8. If I did this, I would also get 3/4. Okay, so I feel confident in saying now that this is a geometric series, and not only is it geometric series, but the ratio of it is 3/4. Okay, so I know the ratio. I know A1. More importantly, from knowing the ratio, absolute value of 3/4 is less than 1, which means that this geometric series converges. Right? It does have an actual sum. So what is that sum? That sum is A1 over 1 minus R. A1 is 6, right? Yep. Oh, wait a minute. I forgot a key thing. I forgot a very key piece. This was negative 9/2. So negative 9/2 divided by 6, so that'd be negative 3/4. 27/8 divided by negative 9/2. So this would also end up being negative 3/4. 81/32 is negative. So this would also end up being negative 3/4. Okay, so actually my ratio is negative 3/4, but that's okay because the absolute value of 3/4 or of negative 3/4 is positive 3/4, which is still less than 1. So it still does converge, but I shouldn't forget that negative because I'm going to need that in my formula here of 1 minus R. So A1 over 1 minus R, so 1 minus negative 3/4, so that'll turn into plus 3/4. One plus 3/4, so I want to think about 1 as 4/4. So that would be 7/4 in the denominator. Multiply by the reciprocal, so 6 times 4/7. 6 times 4, 24. So 24/7. That is the infinite sum. and that's it. Okay, so I didn't give you guys any. I guess I should have put an example. Let me just make a dumb example really quick. Okay, infinite series of -7 to 5/3 to the nth, or n-1. So it looks like it's in the form, it is a geometric series, right? A1 times r to the n-1. But my ratio is 5/3. The absolute value of 5/3 is 5/3, which is larger than 1. Which means that it diverges. Now, what does diverges mean? It means there is no sum. All right, this sum goes to positive infinity or negative infinity. So we only use that the a1 over 1 minus r, if we get to this point and see that it converges. Okay, but if there's a ratio larger than that, larger than 1, the absolute value, then we just say diverges, and we stop there. We're done.